Okay, yeah. So nice to be on the other side of the fence here. I'm going to tell you about some kind of experimentation that I did during lockdown as part of an MSc project that we ran here at Leeds with my student Tiffany Koylass. So yeah, some kind of experimentation with concepts about how to best design a drone-based GPR survey. It's one of these kind of lockdown projects that takes on a whole life of its own and maybe sheds a little bit of interesting geophysical insight. So drone-based GPR, I think it's becoming more widespread. It's certainly, you know, there's a few papers out there, but maybe not too much just yet that really formalizes the process. I would say as a little bit of a disclaimer, it is subject to increasing scrutiny, not least because there's legislation about what you can do with a drone and where you can fly it, but also about emitting radar radiation directly into the air. So anyone who gets inspired by this, do bear in mind that there is legislation out there that you must also be subject to. But of course, there are clear advantages of a drone-mounted GPR system. Survey efficiency for one. You know, you can program a drone flight path and let it get on with it while you do something else. There also might be areas that you simply can't access. So here you can see the USGS deploying a drone-based GPR over a flowing river, looking at the bathymetry there. But you could also imagine areas where you've got unexploded ordnance, highly crevassed glacier fields or something like that, where you simply just can't go. So, as I say, clear advantages. There are, of course, benefits from established practice in the way that we might design a drone-based survey. You can, you know, the sort of air launch systems that are very used within civil engineering here for looking at the integrity of a railway track bed. They are air launch systems to all intents and purposes. They are like drone-mounted radars. But when it comes to actual use of, you know, our kind of typical antennas on drones that you could purchase online, there's relatively sparse guidance on the design parameters, such as the optimal flight height. And so we were asking the question during this project, can we formalize those design criteria at all? Why do some manufacturers or some users recommend a low flight height versus a high flight height? Because there was a little bit of inconsistency and I guess controversy in what would be the best recommendation. So we thought we'd play around with that. We needed a kind of local survey, not least because during the pandemic, the university put an embargo on all kind of significant field operations. And so we needed something that could be done on a relatively safe working kind of way, not violating any of the university fieldwork restrictions. We're working then just west of Leeds, so just there where the star is, and this is in the village of Rodley, which is about 5 kilometres west of the centre of Leeds. There is Rodley shown in an 1847 map. It's, like I say, 5 kilometres west of Leeds. Here you've got the River Aire, and here you've got the Leeds-Liverpool Canal. And back around 1847, Rodley was a hive of activity. There was lots of ironworks and metalworks, lots of canal activities going on in this particular area. Funnily enough, one of those ironworks is called Booths, so it almost feels like yeah, a very close association for me. There's the canal. There's the main road that linked the cities of Leeds and Bradford. This has been slightly adapted now, and so when we look in this area, this is rather a sleepy side street now, but back in the day, it would have been a much sort of busier access route to the canal with you know, lots of offloading of canal boats going on. Now, as I say, it's a local survey for me because there's my house and there is our survey site. So it was all kind of consistent with going outside for just 1 hour at the height of the lockdown. As I say, this once busy road is now a relatively sleepy side street. There's an OK pub just here behind the tree. You can see the canal boats just here. And our survey line that we did is just towards the end of this street. It's about 20 metres long. And before we get into the results and the considerations for the drone-based survey, I'll just give you an example of the data we got with the ground-based survey. So there we have results from a 1000 megahertz sensors and software Pulse Echo Pro antenna system, and you can see that there are various surfaces and diffractions in the ground there. Here's the kind of principal features that I can see. I've tried to highlight with the solid lines things that I think are the base of the modern road surface, so the base of modern asphalt. Towards the end of the road here, that's where recently there was some construction work going on, and I think that that surface there is the base of modern asphalt. The dashed lines are what I think are something to do with the base of older foundations. You can see here in particular that it's made of a whole load of diffraction hyperbole, and I think that they're related to the cobble surface of the old road. Indeed, you can see exposed cobbles between these two vehicles. So I think that's the kind of the background to what we're trying to see, and trying to see how we'll evolve with our experimental drone-based surveys. So getting on to those drone-based surveys then, why is there this discrepancy between recommendations to fly high or fly low? Well, first of all, by flying high or flying low, I mean in excess or less than one wavelength of the radar energy. For both of these regimes, you'd expect that there's some degree of reflectivity loss at the ground surface, but that would be common to both of these, so I'm kind of taking that as read. The considerations in a high-flying drone, though, could be that on the downside, in flying high, you have increased propagation losses through the air. You're simply requiring your radar energy to travel further. Maybe you're also vulnerable to clutter, so in this expanding beam of radar illumination, if you've got things that are slightly offline, then you might expect reflections to come back and contaminate your data. But of course, in flying high, you avoid those obstacles. You don't have to really change your flight height too much. So at least you've got that consistent position, if you like. When we come to low flying drones, obviously there's reduced propagation losses. You are inherently closer to your target. But then there's also this quite strange effect, I think, because obviously there's a big velocity contrast between radar traveling through the air and radar then traveling through the ground. And I think that gives a strong refraction or ray bending effect. So you could imagine that this hyperbola that we're trying to image down here, hyperbola obviously being the bread and butter of a lot of archaeological surveys, rather than having effectively a straight ray going down to that, we've got this really kind of bent thing as the ray path refracts at the air-ground interface. And it's that I want to focus on in the next couple of slides and just show you what I mean by that distortion of a diffraction hyperbola. What we've done is a ray tracing regime. So here we're simulating a ground-based system, and the rays that we'd image a pipe buried at 35 centimeters depth in a medium of 0.09 meters per nanosecond velocity. They're the ray paths associated with our diffraction hyperbola that we all know and love. But when we take the drone to a flight height of 20 centimeters, there's this real distortion of the ray paths, and that produces a hyperbola that looks more like this. It's much more open than the hyperbole that we would normally expect to see and recognize. So is there a question that we would risk not recognizing them as such? They don't look like our common or garden hyperbole anymore. And also, does it mean that the velocity analysis that we do becomes unreliable? If I do a curve-fitting approach to the blue hyperbola, then surprise, surprise, it yields a velocity of 0.09 meters per nanosecond. But if we do the same thing for the red hyperbola expresses a speed that's almost twice as fast. And so when you come to depth conversion, you're going to be a factor of 2 out. And that's a velocity that even compensates for the air gap anyway. So even when you correct for that, you've got too fast a propagation velocity. So that's potentially a real problem for us. Ray tracing is all very well and good, but we also did some more sophisticated modeling using GPR max simulations. Not going to dwell on this, but just to highlight again the fact that for this ground-based system versus here a 25 centimeter flight height, 25 centimeter flight height gives you this much broader antenna that gives you an overestimate of the subsurface propagation velocity. Here, 0.12 meters per nanosecond. We have this finite radius pipe, so the velocity is always going to be a little bit exaggerated, but it's even more exaggerated when we come to the drone. So there are these potential significant issues for imaging diffractions and diffracting targets with a drone-based system. You'll notice that imaging surfaces is okay, but the drone doesn't really lend itself maybe to imaging hyperbole. Let's take a look at the real data domain and with the homemade drone that we made. We treated ourselves to a lockdown barbecue, and we upcycled some of the polystyrene packaging that came from it, because this was the frame, and it looked to me like 1000 megahertz antenna would fit perfectly within it and be able to simulate drone-based surveying. After some trial and error, we have this then manually operated bio-powered drone with adjustable handle so that you can raise it up and down off the ground. You fix your arms in place and you can keep it at a pretty constant flight height, or at least that's what we were pretty confident it was as constant as we possibly could make it. So we went out and surveyed. Just as a refresher, this is the ground-based data. Again, you can see all these diffraction hyperbole coming through here. I'll put on a quick annotation of where I can see these features, and then gradually I'll play through the different data sets as we increase the flight height. Here to 5 centimeters, you can still see the hyperbole there, but they're a bit less well defined. When we go to 10 centimeters, though, the data is suddenly almost extinguished around this area of diffraction hyperbole. You can still see some evidence of this surface over here, but it's starting to degrade. That story is pretty consistent until we get to the really the high flight height. So here, 1 wavelength, and you can start to see that we are defining this surface again down here, but with a collection of much broader looking hyperbole than with the ground-based system, and that sort of bears out the synthetics that we did. There are the two data sets for comparison, the ground-based system and the 30 centimeter flight height. And you see that, yes, you can see something there, but only with the benefit, I think, of seeing the ground-based system. So on the face of it, I think that the drone-based results are pretty poor. I might suggest that higher flight heights are marginally better, but they're all compared to just simple surface-based surveying. Now, is that because I can't build a drone? Now, maybe, and I would like to see what happens when we use an official drone and mount our antennas on that. But maybe not. As I showed you, we can see that reflective surfaces can be imaged to some extent, and it's the diffraction hyperbole that really suffer, and maybe that's irrespective of how well we build a drone or whether we use a proper official one. So maybe there'll be more success not only with an official drone, but maybe also with more directional, like horn type antennas that are being mounted behind that vehicle there. So much more directional than the sensors and software set that we've got. So my conclusion is that for now, until pending further research, I would suggest fly high. I would agree with the kind of 1 wavelength recommendations, but I think there's more to come. It's an exciting field, and I would like to get to mess around with a real drone one of these days. So that's it from me. Very happy to take any questions, and yeah, cheers.
Thank you very much, Adam. Do we have any questions? From my side, I would like to say that this looks like a very enjoyable lockdown. Matt, please.
Hi, Adam. When you were flying it at the higher altitudes, there was some quite strong reflectors at the longer two-way time travels. Do you believe that they were air-based reflectors from vehicles or other metallic obstacles on the road?
Yes, possibly so. So there are a couple of drain covers along the way. They look a bit broad to me to be drain covers, but I think they could very well be reflections from vehicles. Whilst there was the occasional car that came down the street during the hour of surveying that we did, there wasn't any other cars pulled up and actually parked, if you get what I mean. So the whole above surface clutter is staying pretty consistent. So yes, I think that could very well be an artifact of this like wider radiation beam.